Welcome to our next lesson on optimization. Today we are looking at cost and revenue. So you will be able to solve optimization problems involving cost, revenue, and profit using derivatives. So our first example, and we're jumping right into our example. Again, remember the algorithm we saw last class works for all optimization problems, so please review that if you need to. But I hope through some examples you'll be able to pick up on what we need to look out for cost and revenue problems. So in our first example, we have an open top rectangular box has a volume of 250 centimeters cubed. The width of the box is 5 centimeters. And to make this box, we have to consider the cost. So the cost for the base is $2 per centimeters squared, so the area, and $1 per centimeter squared for the side. And we want to know what's the minimum cost for making the box. And one interpretation of this could be maybe you're using two different materials for the base and the sides, so that's why there's a difference in the costs. Or perhaps the base has to be thicker than the sides, so that's why, again, the base costs more. So we have our, I have a diagram here for you for the net of the box. Again, remember there's no top to it, so we just have the four sides and the base. And we have our length, width, and height. So I have L, W, and H as my variables. And already given from the problem, we did have that W is equal to 5 centimeters. So really, I have two undefined variables, L and H, and we're trying to write one of them in terms of the other so that we're only left with one variable. So just interpreting my diagram here, this would be, for example, the width, which is 5. Here we have our length, and our height is these, or let me draw better. So this is our height, and this is also our height. Okay? And I'm just going to rewrite this a little better too. That's width is 5 centimeters. Okay? And we have also been told the volume is 250 centimeters cubed. And this is actually the quantity that is going to help us rewrite the one variable in terms of the other, because we have that volume is equal to length times width times height, which is 250 centimeters cubed. So we can write that length times height is equal to 50 centimeters cubed because width was 5 centimeters. And so height is equal to 50 over L. You can also here choose to write L is equal to 50 over H and then work with H as your variable. I just chose length here, but again, it would work the same way if you use H. And so now the area of the base is width times length, which is 5L. And this is this area over here. And the area of the two sides of the box is width times height, which was 5. And then for height, we're using this, there we go, this expression there. And so I'm left with 250 over L. And so now I have all three of my dimensions of the box using one variable L, and now I can formulate the function that I actually need. So also consider here you have, oh, sorry, we have two sides. So this other side as well is, so consider these two are one size and these two are one size. So the two pink sides are going to be length times height, and that is this over here, which is just 50 because of this expression that we had. And here we have width times height, which is going to be that 5 times 50 over L, so 250 over L. And so now we can write an equation for the cost of the box using that one unknown, because we have the three areas that we need and we know the cost to make each of those areas. So remember, for the pink and the green squares here, or the side lengths, we have a cost of 1 centimeter, or sorry, $1 per centimeter squared. And then for this base, we have $2 per centimeter squared. So my base is going to be 2 times 5L. That's the cost. And for my side length, I have two of the 250 over L, and this just costs $1. And I also have two of the 50 centimeters squared side lengths. And yeah, I could have a one there, but um, it wouldn't make a difference with our expression, but it is one for the $1. And so now just simplifying this, we end up with 10L plus 500 over L plus 100. And now we want to minimize this cost. So we have to find the derivative to find what our critical points might be. So using derivative rules here, we find that C prime of L is 10 minus 500 L squared. And this 100 is just a constant, so it doesn't contribute to our derivative. And now setting the derivative equal to 0, which is this expression here equal to 0, I can just rearrange now. So I have 10 equals 500 over L squared. This is the same as multiplying by L squared on both sides. So L squared, and then these two cancel out, and then I can divide by 10. So dividing by 500 by 10, I end up with 50. So L squared is equal to 50. So then L is taking the square root, positive or negative 5 square root of 2. But because we are working with length, we know that the negative value is inadmissible here. It doesn't work in our context. And I could have had also an additional interpretation here of those domain and or the restrictions on each of my variables. But at the least, I know that length, width, and height are all greater than 0. And using this quantity here, we can have those restrictions. Well, I already know that width is 5, so then LH is less than is less than 5 or equal to 50. And so then we can also have an expression for an inequality expression for each length and height. And so now, using the value that we can use, which is positive 5 square root of 2, we find what the cost will be at this point. And so the cost here, we're just evaluating using our expression for C of X here, or C of L here. Yes, C of L. And we end up with this value, and we will actually rationalize this to be able to solve it. So this is just to show you a bit of like mental math or using mathematical knowledge to be able to solve expressions without a calculator. So this we are just multiplying by square root of 2, square root of 2, and this will give you 100 square root of 2 over 2, which is 50 square root of 2. And so then this expression being 50 square root of 2, we end up with 50 plus 50, 100 square root of 2 plus 100. And now at this point, you can use a calculator to get an approximate value. And especially with word problems, we do want to do that. And so the length that gives us the least cost is going to be 5 squared of 2. And I can actually find this. This is 7 centimeters. And of course, the minimum cost to make the box will be, oh, this should have a dollar sign here, $241.42. And I will just double check here what was I asked. So I was asked, what is the minimum cost for making the box? So all I had to answer was the minimum cost, so I did answer that here as well. And I do want to add one more interpretation here, especially with our feasible values here. So going back to this quantity that we had, of course, we know that length and height are both greater than 0. But for large values of L that I choose, and it may not necessarily be realistic, but it is still possible and feasible. And that's what we are looking at when we're considering optimization problems. So I can pick a large enough value for L, and I would just have that H has to be 50 over that L. And it will be a very small height, but it will still be greater than zero nonetheless. So as long as I have this condition here. And so going back to here, the reason why we don't consider the endpoints, and I highly suggest that you try to graph C of L, and you'll see that the function will look something like this and then go this way. And then you will have that minimum here, which occurs at 7.07241.42. And so that tells us that at L is equal to 7.07, we do have the minimum cost, but again, for S, we choose large enough values of L, our function is still defined, and the cost will still be an admissible value. It will be defined in this context, and it would just be greater than this value here. And because we're minimizing, we just consider this value, and we don't actually check the endpoints here. And so now combining this with what we saw in the previous lesson with area and volume, sometimes just by analyzing the context of the problem, you can skip the part of checking the endpoints if they don't necessarily make sense for your given problem. So now let's look at another problem. Here we are told a car rental agency has 200 cars, and the owner finds that with a price of $36 per day per car, he can rent all the cars. And so for each $2 increase in the price, the demand is less and 5 fewer cars are rented. So what price will maximize the total revenue? And you've actually seen these problems or similar problems when working with quadratic functions where you had x plus something and then x minus something, and then you had to find the vertex, which would maximize or minimize your value or your function. So that's similar to what we are doing here, but now we have derivatives, which is a helpful tool for us. So the quantity that is varying here is that $2 increase. We choose how many times we add those $2 increase in the price, which also will affect our dependent variable, which is how many cars are rented. So let X represent the number of $2 increases in the price of the cars that are being rented. And again, it's $36 per car to rent it out, and he has 200 cars. And so the price can be represented as 36 plus 2x, which is the number of $2 increases. And the number of cars is 200 minus 5x. So perhaps he can rent out all 200 cars, or if the demand is, so again, he's renting it out if it's $36 per day, which is when x is equal to 0. And as he increases the price, he is charging more per car, but he's also renting out fewer cars. So that's that 200 minus 5x. And so revenue is the price of price times number of units. So in this case, it's the price of the car or the price to rent a car times the number of cars that are rented out. So in terms of x, we can write our revenue function as r of x, which is 36 plus 2x times 200 minus 5x. And so here I will just write this in expanded form. So we have 7,200, and I'm just using my FOIL method here. 80. And then I will just rewrite this, and I always write my highest degree first. And then we have 220x plus 7,200. There we go. And this is our x. Okay? And we so this is the part that I was asking, reminding you of with the quadratic, and I do recommend here take a moment and try to actually solve this using the method of finding the vertex. So you already can tell what the roots are based on this factored form. This is the factored form for the function, and based on where the zeros are, you can find the axis of symmetry, which is the x value of your vertex, and it's also at that X is the number of $2 increases that will maximize our revenue. And then finding R of X at that value of X will give you the maximum revenue. And then to find the price, you just have to use 36 plus 2x, yeah, for the X value that you find. So now we're going to try this using the derivatives. So given R of X here, we find that R prime of X is negative 20x from there. And this one is just 220. And this is a constant, so it's just 0. And that's exactly what we have here. Now, R prime of X happens when, the maximum occurs when R prime of X is equal to 0. And this happens when X is 220 over 20. And this is just rearranging these. And this is equal to 11. And so how do we interpret this value of X? What does it mean given our problem? So remember, X is the number of $2 increases. So that means if we increase our price by $22, which is 2 times 11, so we're increasing it by $2 11 times, then we are maximizing our profit. And so this will be 30, for the price, we have 36 plus 20, or 2 times 11, which is 22. And this gives us 58, and this is $58, which is the price to rent a car. And the maximum revenue, how we find that, remember we have to find the number of cars rented, which is 200 minus 5x. And in this case, it's 55. So we have 145. And you can double check here that 145 times 58 will give you 841, or sorry, $8,410, which is the maximum revenue. And you should have found here as well that the vertex form here would have given you 100, it would have given you 11 as your X, and then the profit would be 8,401. Now, one more additional information I'm gonna add in here is that endpoint interpretation here, which we actually do have to analyze for this function. So going back to our analysis up here, given that the cost is 36 plus 2x, we don't really have a restriction here. You can keep increasing this any amount. You can price your cars to be rented at any price that you want. So no restrictions there. But we do have a restriction over here when we have 200 minus 5x. So first, and we also have that x is greater than or equal to 0. So if x is equal to 0, that would mean we're just not increasing our price. So we just have, we're renting it at $36 per day, and we rent out our 200 cars. But we also want this to be greater than 0, which means that this is 5x is less than 200, and it could be equal, or equal to 40, less than or equal to 40. So then, going back here, our restriction would be, or our feasible values are x is between 0 and 40 inclusive. So we would actually check the endpoints here. So we would find r of 0 and r of 40. But when r is equal to 40, then so here we would have 36 plus 240. But then 200 minus 5 times 40 is actually 0. This is 0. So then this is 0. So that means if you raise your price to $116, that means no one's going to be renting your cars anymore. And anything beyond that as well, no one's renting your cars anymore because the price is too high. And so the number of cars you're renting is 0. And so then you're not making any revenue. Now for R of 0, that means you're not increasing your price. That means you just are renting 200 cars at $36 per day, and this is just $72 $8,000. And so we do actually have to have this analysis in there as well to consider the endpoints because we do have defined endpoints here and they do make sense in the context of our problems. It doesn't necessarily give us the best answer, but it does give us an answer that is defined. And so now with these values, the maximum revenue we can get is 8,410, which happens when we are renting our cars at $58. So even though we're not necessarily renting out all the cars, we are making a greater revenue per day. And as a business, you might be analyzing this and thinking, oh, well, also that's great because renting out fewer cars means there's less restraint or less use of our cars on a daily basis. So that means maybe there's a longer lifeline of cars. And then that would also be another function and analysis you bring in. And that's why businesses will be optimizing their units, their quantities in a lot of different ways in order to maximize their profit or minimize their costs and a lot of other factors in there. And so we're going to look at our last example here. So a consultant determines that the proportion of people who respond to the advertisement of a new product after T days of marketing is given by the function f of t. The advertisement reaches 10 million potential customers, and each response to the ad will, on average, result in a revenue of 70 cents. And this excludes the cost of advertising. The advertising cost itself is $30,000 to produce and a further $5,000 per day to run. So we have a lot of different quantities here, and we have to definitely analyze our word problem in order to produce the function that we actually need. So first, let's just, we're asked to determine the limit of the function as t approaches infinity. So as the days go on and more, so remember t is in days. So as more and more days pass, what is the proportion of people who are responding to the advertisement, which is given by f of t? So how many people are responding here? And so we see that as t grows to infinity, then this portion, which is e to the power of negative 0.2t, is approaching zero. So it's getting smaller and smaller. And so this limit is resembling 0.7 times 1 minus 0, which is just 0.7. And interpreting this means that if we advertise indefinitely, so as time is approaching infinity, so day after day, then eventually 70% of the people or that population will respond to the advertisement. Now we're asked what percentage of the population has responded after 1 week of advertising. So this one we're just interpreting with f of t, but t is 7 here. So after 1 week or 7 days of advertising, we have f of 7, and this is just substituting our value and evaluating. We have 0.53. So again, interpreting that, we have that 53% of the population has responded after 1 week. So you send out this advertisement, and after 1 week, 53% of the people have seen it and responded. And again, if you keep this advertisement up indefinitely, eventually 70% of people will respond. And now we're asked to write a function p of t, which is the average profit after t days of advertising. And we want to know what the average profit is after a week. And average profit, this is that instantaneous rate of change. And after a week, we have t is 7. So remember also, profit is average revenue minus the cost. So first we want to know what the revenue is and also take away the cost to find our profit. So in this example, we're told that the advertisement reaches 10 million people. And so the number of people who respond to the ad after t days is given by, and this is just going back to here, it's f of t of that 10 million people. And so the average revenue here, we were told here it is $0.70 or 70 cents. And again, we're not analyzing the costs yet, so just 0.70. And now my uh, just my revenue, we're not going into profit just yet. Revenue of T is given by the portion of the population that the advertisement reaches times the revenue from each respondent, which is 0.7. And so 0.7 and 7 is just 4.9. And then I have this quantity left. And so going back to here, this is now consider if, again, we keep this advertisement on indefinitely, then of those 10 million people, uh, and again, this is going towards zero if t is going towards infinity, then 700,000 people, or sorry, 7 million people have, 7 million is 70% of the 10 million people have responded to the ad. And but we don't know now what time, so we want to have just an expression, so we just leave t as t. Now, the advertising cost, C of t, we were told there is a $30,000 flat rate and a further $5,000 per day to run. So consider this, for example, it takes $30,000 to create the billboard or the design, pay the people who are designing it. And then any day that you're paying rent for example, this advertisement to be on a billboard, it takes $5,000 for the cost. Or there could even be digital advertisement. You might be paying co websites or promoters to be advertising for you, and it takes $5,000 per day. So your cost is $30,000 plus $5,000 T, which was the number of days. Now, our profit as a function is R of T take away the cost, which is C of T. And so all I'm doing now is just substituting these two functions here, which was R of T and C of T, to get P of T. And we were asked to find the average profit after 7 days. So you can now, so this part first, we are just substituting to find P of 7 here, and you can confirm that this would be $3 million, 620 or $3,627,000. And now we have that if the advertising budget is $200,000, how many days should the advertising campaign be run to maximize the average profit? So now we have a bit of, we have to do an analysis for feasible values. So given this advertising budget, we have that C of T has to be less than $200,000. And so inputting this into our function, we have $30,000 plus 5,000 T is less than $200,000. And just rearranging here, we get that T is less than 34, less than or equal to 34. So sorry, there should be an equality here as well. So our advertisement has to run less than 34 days or 34 days. And we also have this as well. We know time, the number of days has to be greater than 0. And so we are left with this overall inequality. And we want to maximize P of T, or profit, on this interval. So first, I will just find the derivative here, which we're just using derivative laws. So take a moment to analyze those. We also have that exponential in there. So we know that the derivative of the exponential is just itself. And so our simplified P prime of T is this equation here. And now we find the critical points here. So P prime of T is equal to 0. We want to solve what values of T produce this. And here I have, because I have that E, I do have to use my natural log here, and I will find that T is approximately 26. And so now we want to evaluate the profit at T is 26, so 26 days, as well as the endpoints 0 and 34 days. So please check that you will get these profit outputs. So after 26 days, we have 4,713,000. At 0, we have actually just the cost. We haven't reached anyone, so it's all just the cost that we've paid for the advertisement and no revenue. And after 34 days, we have $4,695,000. And I just interpreted that for you. But we see clearly that the maximum average profit occurs after the after the ad runs for 26 days. So very close values, but this is still our maximum. And that's a wrap on our lesson on cost and profit and revenue. And if you have any questions, don't hesitate to reach out, and I'll see you all next class.